Okay, everyone, welcome back to the second part of our lecture for today, MPI Parallel IO, which is one of the really advanced MPI techniques, but at the other hand, also a very different technique than the ones you have actually explored before. We have been starting with point-to-point communication. We have done collective communication. Then we thought a little bit about the Cartesian communicators, the splitting of communicators. So all was around communication in the sense of transferring data from A to B for processing, for computing, and so forth. What we left out in this perspective is that sometimes we don't want to just communicate a variable maybe to the memory space of another one. That we have learned is mostly here in our context a distributed memory. Otherwise, I probably would rather use a shared memory available because it's faster. But in our device, we have also in the HPC systems something we called I/O, which stands for input output. I think that's pretty obvious, but that what does it mean exactly, right? So, and why we talk about parallel I/O is really something we will see now in the second part of this lecture. So it complements essentially the ideas that we have seen before, that several times we have to shift the view how HPC is done. We have seen in the first part when we have just a computing focused perspective, you see that here on the course, we always think about these interesting fellows, what many people do. So what is the processing speed of this? Perfect, okay. But we also learned in the second part, in the first part, that if I have just a little bit of Ethernet connection there, instead of InfiniBand, as you have learned from the video, with very, let's say, low latency interconnects, then essentially I'm back to having different servers, maybe interconnected with Ethernet and not really a HPC system. So another perspective, the interconnects really play a big role. And again, like we do the shift in this perspective, putting more emphasis on the interconnects here, we can do another shift of the view where we say the HPC system is all about data. Because what do I want to do with this HPC system, right? Usually what I want to do is to compute something over time. I have some physical laws. I want to do this with numerical methods, and then I have some data computed and I want to put it to disk and then do my data analysis on it or my statistics on it, and then, would have some scientific evidence or some research done. Or in engineering, I want to have something simulated, crashes and so on of cars, something we will also do. But in the end, what I want to do is to analyze these crashes, how we can better the materials, how we can influence the design of cars, of airplanes to make it better. And in all of these is data involved. So meaning that not only in this deep learning, AI, machine learning, there's data involved, also in the physics is data involved. Of course, this is something we call these days with the magic word big data, right? So of course, if you have an interesting website, you can look in what that then has to do with parallel processing. But the key essence to take away is that big data was always there already in simulation sciences since decades. It was always big data because HPC was so much at the forefront of computing that normal systems could never directly handle it. Hence, people at that time already had ideas about how to influence the I/O to a manner that this becomes scalable too. Only when I increase more and more computing again and again, I will enter the parallel processing bottleneck, essentially, of saying, what do I want now to do with all of this data if I would basically have not really thought about the I/O? And that is what's really about this parallel I/O techniques. We have to look back what I/O really means to really fully understand that. So they're kind of really time-sensitive factors within this HPC. So a lot depends on them. Memory is an interesting factor. We know it's very fast, but unfortunately also very limited in space. So big data and memory is quite hard to do. Even with HBM, with new GPUs, which have, let's say, quite interesting memory setups, still to have the same, like a complete 500,000 core simulation all put in one memory of a GPU is unrealistic. So we need to have the disks, SSDs these days. And then when you come to tertiary storage, maybe also large archives behind it, right? And then you have, again, essentially the disks and then memory. So this is something where, instead of using MPI for just communicate between these distributed memories, We also have to think about what happens now if I want to end my application. If I have done my results, my numerical weather prediction has ended, I know what the weather will be. I just have to do some summary statistics. How will I put this to disks now that I have data in all of the different memory spaces distributed across the cluster? How I will now put this to the disks? Another factor that influences this is so-called checkpointing. So you can imagine when you want to compute, for instance, the NWP, the numerical weather prediction over, let's say, a certain domain for the next 24 hours, this requires enormous computing time over, let's say, many hours. So when there's something happening to this machine in the meanwhile, I lose all of that. Let's say there's a disk error or there's a CPU overheated and suddenly I cannot use this particular rack anymore because there's any other idea of kind of fault which could happen. Then I suddenly have the problem that the whole simulation is, down to drain. Hence, people have thought about this so-called checkpointing, that every now and then in certain iterations, it may not be every iteration, that would be maybe overdoing it, but in every certain iterations, you have something you would say, you save the status to disk. In other words, for you guys which are maybe gamers, you save the game, right? So you save the game how the simulation is right now. You drop everything to disk, that in case of a fault, you can start there. You know the iteration, you know the physical parameters, you can start from there. Because the physical laws in the end will not change. They are already encoded in your program, in your application. All what matters is the data at that particular time, at that particular iteration. So this is in disk, and this is called checkpointing. So you see there are kind of practical implications why we need to think about I/O also, and not only about communication exchanges when it is about MPI. Of course, when you go to the extreme, sharing data then across different clusters, let's say in the cloud and so on, then it's something which actually leaves the space of this course. Here we have a complementary course to this one called Cloud Computing and Big Data, where we talk basically about lots of different factors like machine learning, deep learning, but also then much more in distributed file systems, distributed areas of computing. So here we remain in the realm of saying we are in one big cluster, interconnected, and I have lots of distributed memory with data. So this immediately brings us to the question, what is the connection between all of these processors with a disk? And immediately it becomes clear that the interconnect to this, of course, plays an important role in this, but also the pattern, how I now basically do something with the disk, is now a very influential one. When you think about this kind of parallel computing, they're all in parallel develop this data. Now, when I think about the data that I could store, it will be maybe one big file summarizing all of this. But as you will know, basically from your normal opening maybe of your Word document or so on your little laptop, you would have a kind of a serial I/O. You cannot just, let's say, open the same Word document 6 times and then basically at the same time use different windows to influence this file. It will give an error. It will usually say it's already used by the other publication, or it will be opened in a read-only manner. Things like that happen, but you a little bit know already from your laptop to better understand this, right? So it's a little bit an analogy here. So we need a more smarter mechanism of thinking about that the access to this data file or whatever it is, what I have here on this, let's say, disks, away from the compute nodes, which is basically a bit more smart than doing it in a serial fashion. And this is really something called the I/O challenge. Because a serial access would be not very good. It is a shared access by so many different multiple processors. And immediately you can see the orders of scale here. If you have, let's say, as we have seen in one of the weak scaling plots or strong scaling plots with up to 500,000 cores, then this could have a big difference how you store your data. In other words, it's such a, let's say, bottleneck that you have to really think about to make it also high performance. And this is something where people have thought about. So there are different parallel file systems now available. And we talk about more of these technologies also, interestingly enough, in the cloud computing course, where we think much more broader about data and more in detail. But basically you see that these kind of parallel file systems have one key differentiator, and this is it supports really this concurrent file access. Again, because it's important, concurrent file access. In other words, at the same time, different processors can write in the same file, right? And this is something where your normal file system on your laptops running Windows and so on are at the end. They cannot do this. They basically have different mechanisms doing this. And there are many different advantages of it, because you can now imagine there would be a direct flow of information, reading, writing to this, basically to these files. You have more or less a really combined bandwidth of doing this, and from all the physical drives. So it's a really very good idea to really make this much more faster when you want to write and read, to have this kind of parallelization. Of course, there's some disadvantages. Basically, you need more ideas about rates and different ideas how you do kind of data protection and so on. But these are also topics we cover much more in the cloud and big data course, and not so much here in the high performance computing course, because they leave the space really from the application domain more to a data management domain. So what are examples of these parallel file systems? And this is a bit loaded because there are not so many around that really are there. It is loaded because the first one I'm listing here, which was called a long time the General Parallel File System, GPFS, is transitioned in the light of big data from IBM to something they call Spectrum Scale. It's now basically the heart of big data solution in IBM, basically having a very powerful GPFS and parallel file system implementation that was used for years in HPC centers worldwide. A bit more open source, and with this, of course, come a little bit certain drawbacks maybe compared to the GPFS IBM Spectrum Scale. But of course, in a way, it's free. So then you basically have a file system with Lustre that has essentially the same idea of doing what also was GPFS doing. But of course, then there's a support idea and so on that you always have to think. And there are some others around, like the Parallel Virtual File System or so, here and there a little bit older. But if you want to look a little bit what's happening now in HPC, it's really often the Lustre or the GPFS IBM Spectrum Scale today. But all of them share several different concepts, and these are the concepts I will now allude to when we also come back shortly to MPI, because we want to see how it practically implemented now if we would have a parallel file system. So in UTUN, we don't have that. So when you work on this in assignments, you will see it's not really completely supported. It cannot. But if you would have a parallel file system really there at your disposal, like the IBM Spectrum Scale, you would have then the following situation that you see here on the left-hand side. You would have different, let's say, threads that will work all on some parts of the applications, but you would always have this kind of two different mappings where you have this kind of single logical file where you believe you still actually write in one file, which is not completely true. It helps you as a developer to think about only one file, but indeed it's actually going through different IO nodes and then having, let's say, different so-called blocks put away on different really kind of underlying physical IO nodes that you really have. So in other words, when you think about how this is stored, you see here this kind of blocks from the compute nodes, and you push this to some logical files, it will end up in some form of an IO node where it's really then, let's say, stored on disk. So what you write there in the, let's say, MPI space, in the application space, is one file, but of course underneath is a logic to keep it separate, because it needs to be separate also, because also the storage, of course, should have different nodes, should have different capacities, and mapping then this would be, of course, something where then the parallel file systems idea comes. But on the other hand, giving you the usability of this convenient one file that you just write in. With this, we are at a so-called striping technique as well, where basically you see here striping factor means how many really disks you have in order to save your data. When you saw the lowest block that we just had, you can consider maybe a striping of here this time of factors. I guess every second should go to a different disk. Of course, this really depends on the way how many disks you have, how you basically do your application. but this is something also you can actually optimize a little bit to get some application performance out of it when you use MPI-IO hints, something I will come back to later in this lecture. So when we now think about this parallel file access, how could that look like? In Unix, we have the inode. Here we have something like, this file control block that really has, everything around the file system kind of inside this, which has then the idea of mapping it from this, let's say, logical file name that is just for us as developers or application people important. And it maps it basically to this file control box. In the parallel file system, then you would have every IO node that actually manages some parts of the blocks available. And basically every of this has then a file control block over every of this node to know essentially where are which files. And in order to locate then a file, you really need, a kind of certain directory structure to keep, let's say, the follow-up, the metadata essentially, and in order to know where you can basically find the file again in order for application people to read, for instance, again, once you write it, right? Because you do everything on a logical file, that's all what we know as users. And we maybe can give a striping factor down there, but we don't know anything underneath about, the direct file control blocks and so on. So there needs to be some mechanism that is then basically encapsulated in this parallel file access. And this is a quite interesting part. And when you're writing, you can imagine that this has lots of implications. And one of this is this so-called sequential consistency. When you think about sequential writing to these different files, you would have two processes in a way on different compute nodes. And then you could think about that, of course, now the time when they really have access to the IO node matters now. So that basically the question is, could all of them write in the same manner, right? Are all the writes or their portions in the same order? Because we never know who would be first, right? And when you actually stripe already the file over many different IO nodes, then it's of course very hard to do so because you then have different IO nodes that actually are independently working as well. So there are different, of course, solutions and how you can avoid this typical sequential consistency that you normally would love to do. Your laptop essentially, again, sequential consistency, just opening one Word document and all other processes just in read-only means it's clear who is here the winner. It's the one you opened and have write access. All others just have read access. So automatically this is solved. It's called locking the entire files, but that's not what we want, right? It prevents parallel access, of course. So this is not the option. And then there are different, let's say, intermediate options where you then would have, relaxed consistency semantics so that you as a developer are much more responsible. If that's a good writing to a file, you can maybe check this when you read the file again and see, okay, it has been all perfectly stored. Or you basically have some certain file partitions, which is then a kind of, again, medium idea to the problem. The full main kind of idea to this problem is essentially a bit addressed by saying we just have different file pointers still opening the same file, right? So when you do this, of course, you have here the interesting idea that you have, again, two threads working maybe on a certain part of the file, and then you kind of have a shared file pointer. And it's, of course, very common when you have shared memory, then it's very easy. But if you have then basically the seek and write operations differently, you cannot come up really to some actually problems by doing so. And the key way to losing this kind of bound between this is to have, again, separate file pointers, so on, where you then basically have an improvement of the usage where you can do this and then get essentially the idea of really parallelization out of it. But working with this requires really a little bit of practical experience. So that's why also parts of the practicals will be a little bit working into this direction. And then you have, of course, different optimizations and dependencies. again, think about that, as I said, the I/O is nothing else than, from a certain perspective, parts of the network. So you have to go and send the data, this time not between the different CPUs, but to disks. So here the question, as we said before, goes when essentially I will store in the iterative process. Who is storing the data? Is it just the master process and all the other worker processors, they are idle? Or do they do some computing? Or so what is the pattern of doing actually this I/O? Is everybody involved or just a subset of processors involved? What about the hardware underneath, the rear cables, essentially getting a link to the disks? So all of these are questions which are, influencing the performance, and parts of them, especially also the programming parts of it, is something what we will also look in lecture 8, much more from a performance perspective. Here we do more a perspective on, let's say, the practical implementation, because it will be also one part of the assignment just to play around with this. Again, we don't have really a parallel file system here, but we will see basically in Newton that still we can use MPI-IO there. And to understand I/O is now the important factor. Again, when you think about MPI, it was all about message exchanges so far. And you should keep that into your mind that this is, of course, a very important part of MPI. But what we also need is kind of this different I/O that every now and then a processor needs to store something to disk. So the interesting thing is it has different operation modes. Again, very similar the way how you do the MPI-IO, of course. Now the look and feel is indeed like MPI before. So we have kind of collective operations, right? We want to do not every little processor itself doing one thing. We want to do it for a collective set of processors doing all the same thing, but maybe, in different parts of the file. We have a blocking mode, so we wait until I/O is written, for instance, or we have a non-blocking mode, so we can actually asynchronously perform computation while we still, write and read, because essentially you stress other parts of the system, right? The CPU is not necessarily anymore required. You just read from memory, put it to the I/O, and then basically the processor in a way is free and can be also again used for computation with overlap to, storing. So lots of different ways how you can work with this. And of course, I just shed here light on a couple of more conceptual aspects around it, mostly in the idea of, again, thinking about the files that are involved and what means now parallelization. So to realize an MPI this, we have to think about parallel I/O. But to understand parallel I/O, I think there's an important part of this to understand now again what serial I/O would be, right, if you would do this. And this is something which absolutely don't helps here. If you have a small application, like maybe some of the assignment applications we have, in theory, you could implement this, then it's maybe not the biggest problem if you have a very small problem. But of course, it's really not a scalable solution if you go to really large problems. If you think about now, we have here, instead of 5 processors, lots of, 500,000 processors that we have seen in the one particular application, and they're all exchanging. And maybe at some point in time, we want to collect all the data. Then we have here one selected master that is responsible for the I/O in order to save all the data to disk. This might be even unrealistic because the particles have all memory space they occupy. Sometimes it's even memory bound problems. So essentially this P5 could not even handle all the data. And you can immediately also see, just to wait for all the processes here, so that this poor fellow here is writing everything to disk, is an enormous load imbalance that we don't really want to do. But actually it captures the essence of serial, because it's not other way possible. You have just the disk, it has one file, I want to put it in, and I do it as I read it as one processor. It's serial, so I am allowed to do it. There's no problem. No problem of consistency, of course, here. So let's just write, but it will take not only very long because we have just one processor and one stream doing it. Also, all other idle processors here are a very inconvenient way of using resources. So what could be the solution? The solution would be clearly now, well, we have thought about this. So I write locally all my I/O files. So essentially individual files, right? Essentially Now thinking about that everybody has its small status on its own, it seems to be a kind of straightforward way to do this. And in a way, it's a bit limited by the file system capabilities. So if you now think about, again, you're much more than 5 processors. Here, it's pretty obvious you can probably do this. You have all the different message exchanges. At some point in time, someone wants to do checkpointing, and someone says, well, I have all my different local ones. Let's put them to disk. And as the disk is, connected to all the processors, it means creating 5, kind of files. Now, the problem is if you scale up. This means 500,000, as we have seen in one of the, I think, weak or strong scaling plots. There, basically, you had the idea that you have to scale this I/O pattern. And when you now think about that the disk has to create 500,000 files, you can imagine that this is a key limitation. So essentially, your file system will not be able to do this. Right, so you can also create this and measure this. So how long it will take to get a certain contention, really, because a file system, let's say like a Linux file system or Unix, creating so many inodes, which are then carrying the essence of the metadata for the files and so on, is simply breaking if you increase more and more the number of CPUs. So in this sense, you would even have the problem that the disk cannot really keep up with all of these I/O requests because they didn't have yet recreated 500,000 files, which is a big overhead for the disk itself and the file system, of course, managing it. So also this sounds plausible, sounds like a nice idea, and definitely easy for the application programmer to think about because everything is so natural. Every process has its own I/O and it remains in its own file, beautifully separated. I can always load this and so forth. But basically, the problem here you have is it doesn't really scale. So instead, people have thought about this parallel I/O, which is really a shared file. And the file is essentially really on the disk a kind of file that you would write in. And the file system underneath will then take care of the blocks, as we discussed previously. But from the file system perspective, nothing prevents us to write this file. But before I just, write this directly to disk, I have certain positions in the file so that I have a kind of shared access or concurrent access, which means really everybody has its own little part of one file, but it's exclusive, right? So nobody of the other processors is considered to write in this portion at the same time. And this parallel I/O is essentially the shared file. And this is exactly how MPI-IO is working with this. So basically, it's a standardized version even. So Parallel I/O and MPI-IO, you have different ways now how to use it. But the file formats which have then and carry this specific portions of the single file are even these days standardized. And 2 major standards in this parallel file formats are HDF and NetCDF we come back to. But this is a nice idea now, so how we see that realized. And of course, there will be demonstrations around this. Of course, as you can always assume, it will be around Practical Lecture 5.1 when we see this. And of course, we see this also later on in some of the applications, because I/O is an inherent part of every application on the supercomputers today, and especially also in AI. So an example of AI, just for the completeness, would be, for instance, just dumping a deep learning net, right? We have talked about simulations, numerical weather predictions. Think about a deep learning network instead, when you want to have some deep learning image recognition and you have trained the network now over 10 hours and it's time to drop it to disk. We have all the weights in the deep learning network between all the different, neurons to store that you trained, over all the iterations, over all the batches and epochs in the last period of the 10 hours, maybe you trained it. So the same way, you need I/O to store all of these weights and a little bit about the topology setup of your deep learning network as well. How many maybe convolutional layers, what is the feature maps and so forth. So, but these are things which will come up in subsequent lectures when we have, more about machine learning and deep learning, which share, of course, some of the same challenges, which means how you can quickly dump things to file, and the other way around, how you can quickly read aspects from the file. So here we have similar like in serial programming an MPI file. So essentially a file handle, right? So something where I need to know as an application developer, what is the name, where it's located, and so forth. I get certain info about these files, basically that I can query when I do MPI info create. And then we have this MPI info object that basically provides lots of information for MPI-IO, and I can manipulate this. Here, let's say the first part we do here is open a file then. And this is an interesting thing because it can be, of course, very much now depending on for what you use essentially this file. You see already it's basically creating it, maybe if it's not existing before, but much more notably, you can here have the different modes. And here we have an MPI mode read write, but you also have read only and other aspects. So this is of course something to think about. When MPI already knows it's just read only, then can, let's say, have different aspects prepared, then already have also the write access. And it also protects it from other writes and reads and so forth. But these are things which we have much more than in the practical aspects, in the practical lectures where we talk about. Of course, think about when you write a file, still what you want to write in the file is a variable. So here we have an integer buffer of 10 as an example that we basically have here and want to write to the file. It's essentially an MPI int data type, and all of these information given the file handle where to store it is then something I can do. And then I get the status out in order to query it again. It's not pointed here. So what we can always query, how much was basically this happening and so on. There's a write ordered, which is then basically have different aspects, how you exactly have the rank ordering in the file. This is also something best explained when we have then the practical demonstrations, but you can imagine this ordered will have then a very proper way of seeing into the file in a really rank perspective, while in write, we really purely write to a file. And then we have to close the file at the end. Basically similar like you would do also in normal serial programming, to release the file handle from being open to inform the system that this file is now closed and maybe can be opened by another application or by another simulation, maybe. Now, these are the, let's say, core conceptual aspects. And of course, there are much more to it and many different functionalities, but this is how MPI-IO in general works. Now, what I also was saying is there are some aspects around it which makes it really the solution modus operandi these days. Some of them we will also have in lecture 5 to have a bit more influence in this. You can imagine that this parallel IO via the IO middleware is essentially standing for 3 different things now. We have a high-level IO library, which we didn't touch yet. So we only talked about the IO hardware. These are the things, the optical cables, the IO nodes that I have. We talked about an interesting smart solution called the parallel file system that already assumes concurrent file access, right, to all of this IO. So this is being prepared for parallel streams into one file and so forth. And the way how I deal with it would be MPI-IO, right? So I have some write, I have some read functions. I know how to handle a file. I got a status. What we didn't talk about is, of course, that this standard, because MPI is a standard, can now give rise to other, let's say, higher level IO library standards, which, can be put on top of MPI-IO to then really have some interesting standards in the different application communities. And this is a sphere then really of such kind of data or standardized, let's say, parallel file formats called netcdf or the hierarchical data format as 2 examples. And then, of course, you can imagine each of the different application communities already made that choice, which of them they are supporting in different versions. Already these climate simulations, they require this and that particular library. So we will come back to this in lecture 5, but also, of course, when we have then our application use cases essentially at the end of our HPC course, we will also there come back again and again how we have their IO implemented with either netcdf or HDF formats. As a short appetizer to this, I brought you another data science example here because it's about data, but could be also simulation science, of course, in both ways. This kind of hierarchical data format really matters. The way how we use it is really essentially thinking about this clustering, the parallel clustering I was alluding to, and that we will basically look into one of our lectures about machine learning and data mining more closely, where we there have really an idea of having a big space. Here you see between all of these number of cells, and then we want to essentially basically do a clustering, meaning we want to create groups from those points or data elements which are close to each other. But it's, let's say, over this different spatial grid parallelized. So I really are in the domain again of having here different cells. With the cells, you know already there's a problem of essentially having ghost cells requirement. So if I want to have this different halo regions, we have to merge halo regions. We perform a local kind of scan and so forth. But of course, to get the data inside this, we need some way of getting all the data in. And here we have, for instance, a hierarchical data format way of actually transforming all of this, what you see here from this kind of points here, which are a little bit artificial, up to our neuroscience applications we do. It's the same way they're using the HDF format in terms of position, in terms of the aspects of the different cluster, you would say the cluster identities. You can imagine once this is computed, you know this is one cluster, let's say cluster 1. This would be probably one cluster, cluster 2, and cluster 3, cluster 4. So basically these cluster identities can be then assigned to every data element to know in which part of the cluster you belong, which then in turn can be used maybe, for instance, here for the visualization of all of these cortical layers in the human brain, which are then responsible for different functions in the human brain, giving the neuroscientists then a better idea in terms of an accident, maybe what happened to, you know, parts of the functionality of the brain. But the core idea is really we are reading here from a HDF file, which has all the locations of the data, let's say here on a 2D spatial grid, but of course the code itself is also parallel, so, and also scalable to different dimensions. So we can also have 3D, for example. But then we basically also store the information back to the HDF file, and we do so by increasing the number, of course. And then, of course, at the end, basically, when we have all of these different clusters computed, we basically can also then put this to disk again with HDF5. More about this then also in our lecture when we have Parallel IO explored in the context of machine learning together with MPI and so forth. We already were saying this is already, you know, this DB scanner kind of hybrid application where we not only use MPI, we also use MPI and OpenMP, and in context of this also Parallel IO. Right, so this is all also I wanted to say essentially about Parallel IO, and admittedly these days with all the different topologies, with also the different architectures you've seen the modular supercomputer, we can have maybe complete different lecture series about Parallel IO, tricks and tips for it. As I said, the hints are quite important, and we will come to this back when we also have a little bit then the practical lectures related to this lecture and the next one, which are kind of a little bit interlinked with each other. So more examples of MPI indirectly will follow in lecture 5. To really understand again the difference between basically serial processing and parallel processing, how this is now related then also to Parallel IO, I brought you a very, let's say, small funny video in a way, but it actually captures very nicely and quick the idea of why Parallel IO is also important and not only parallel processing, because this might be a hindrance or limit. Okay, just a small comment to the video. Of course, there were prices between different companies. It's not what we in the university are really interested in. Still, the idea of capturing the essence of Parallel IO and this throughput was a very nice illustration here, also showing you the different aspects in context. When you also then have multiple servers, what you always have to think about, that in high performance computing, we don't stay just on your local setup, you have the effect multiplied by many, many different processors. And if you then have, let's say, this poor guy that is representing serial IO and has to go through all of this, this would be very tedious, especially if you arrange something like 500,000 cores. So in this setup, I think you have understand with this video, hopefully, what Parallel IO is. You have understood that MPI-IO can be really used for it in a very, let's say, convenient way, because we have MPI essentially in the same way used. We have collectives, we have the kind of idea of how to embed it, and we will see this also in the practical lecture 5.1, after we have then seen a little bit more conceptual aspects of lecture 5 the next time.